Hello guys, in this video I will explain you some basic concepts of aerospace aeronautics, and also I'll give you a brief introduction on how to build an RC aircraft and the electronic components inside it. So let's begin. So to begin with, you need to know some of the main important parts of an airplane. So here you can see a fixed wing aircraft, and the main important parts are the wing, the stabilizer, the vertical fin, and the engine and the fuselage. Control surfaces, the control surface which tend to change the orientation and position of the aircrafts are the control surface such as flaps here. The main use of the flap is to increase the lift at very low speed, and also it gives some amount of drag which slows the aircraft. So these are the two flaps. And usually to talk about flaps are usually deployed during takeoff and landing. During takeoff, flaps will be set to either 10 or 20 knots, but during landing, flaps will be deployed to the maximum in order to reduce the speed of the aircraft and also to gain more lift. So this is another control surfaces for roll of the aircraft. I mean to roll to the right or to the left. So this is one aileron and this is another aileron. And this small part which you can see here, this called as spoiler. It is written that it changes lift, drag and roll. So spoiler is a very usual component, an important component of glider aircraft. It serves the purpose of reducing the speed suddenly. So if you have a problem of overspeeding of aircraft due to some problem of, if you need a sudden landing, emergency landing, and your speed is not set to the landing speed, then always you need to extend the spoilers or deploy the spoilers in order to have a sudden change in the speed. So this surface which you see here is a vertical fin or vertical stabilizer, and the small black surface behind this is called rudder. So rudder serve the purpose of changing the yaw, I mean to turn to the right or to turn the nose to the right or to left horizontally. And usually the motion effect caused by rudder is also dependent on CG. That is, if you give a small roll using these ailerons, then according to the position of CG on the aircraft, either it is forward or to the backward, the aircraft tends to yaw to the particular direction of roll. But in most of the aerobatic aircraft, the CG is very neutrally stabilized, so that each control surfaces serves for only one purpose and not multiple. And another last control surface is the elevator. This is the elevator, the shaded portion, and this whole surface area is called horizontal stabilizer. So elevator is used for pitching the nose up or down. So when the elevator surface are extended up or moved up, the aircraft generally pitches up, and when it is pushed down, the aircraft generally nose of the aircraft moves down. and these are the two engines. Overall this model is jet model, so these are turbojet engines on the underside of the wing, and also this is the fuselage. Here is the cockpit, and also there are some other parts like winglet. Winglet is a small extension of the wing vertically at the tips in order to increase the lift by reducing the drag caused by vortex. Vortex is nothing but due to the pressure difference between the upper and lower surface of the wing. At the tip of the wing there will be the air will be pushed around this in a roll action, so the winglet blocks the roll and increases the lift of the aircraft at the tips. So the next slide is about fixed wing aircraft, and the basic forces which are acting on a fixed wing aircrafts are the weight. This is the weight component, which is mainly due to the it's only due to the gravitational force of the earth, and the lift which balances the weight. So the lift component is due to the aircraft shape of the wing of the aircraft, and some other aspects such as angle of attack. So you will have balanced flight only, balanced vertical flight only if this lift component balanced with the weight. So other component such as thrust, which take the aircraft into forward motion, and drag is a friction component due to the friction between air and the surface of the aircrafts. So when all these components such as weight, lift, thrust and drag are well balanced, then the aircraft is said to be in neutral position or a balanced position. So these are the three axes of the fixed wing aircraft which I mentioned earlier. So yaw is the horizontal motion of the aircraft to right or to left. Roll is the motion of aircraft along this axis to the right or to the left, and pitching is nose is a motion which takes the aircraft nose up or down. So these are some of the terminologies associated with the wing. So when you see a wing from the side, the shape of the wing is called an airfoil. So this is the basic shape of an airfoil. Here you can read some of the terminologies associated with the wing, such as the length from the tip to the trailing edge is called a chord line or a chord. So the maximum thickness is called camber. So this rectangular platform which you can see is the wing platform. It's a basic shape of the wing when you see from the top. The length of the wing, overall length of the wing from the tip, one tip to another tip, is called the wingspan. Wingspan. So this is the chord. The breadth of the wing is generally called as wingspan. So aspect ratio AR, it is defined as here it's like a square by a, but simply you can define it as ratio of length of the wing to the breadth of the wing. So this is dihedral angle. Dihedral or anhedral angle is the angle at which the wing generally or the wing tip raises either up or down of the horizontal line. So if the wing is said to have a dihedral angle if the wing tip points up above the horizontal lines. If it has a dihedral angle, then the wing orientation will be down, like as you see in the fighter aircrafts like Jaguar such aircrafts. So usually diagonal angle is used. They serve the purpose of stability of the aircraft, and angle angles are used for maneuverability. Usually, sport aircraft uses zero diagonal and zero angle, or a straight wing platform. These are some of the shape of the wing. So this one of the rectangular wing which I told earlier. This delta wing, and this wing which is usually suited for passenger aircraft or jet aircrafts. So here you can see a graph of lift versus angle of attack. I already told you that the component of lift is usually affected by the speed of the wing, the shape of the airfoil, and also on another main thing that's called the angle of attack. So angle of attack is nothing but the angle between the horizontal and the base or the chord. Yeah, the angle between the horizontal line and the chord of the aircraft. So if the leading edge of the aircraft is raised by a small angle compared to the horizontal line, then the aircraft is said to have a positive angle of attack. So on the x-axis we have the angle of attack, and on the y-axis we have the lift coefficient. Lift coefficient, one of the main aspect which tend to change the amount of lift of the aircraft. So usually lift component is the lift of the aircraft is generally depend on lift coefficient, the speed of the aircraft, the surface area of the airfoil, and such other parameters. So as you can see, when you increase the angle of attack in this direction, the lift coefficient increases until this tip, and later it tends to decrease suddenly, so that we can say clearly that the angle of attack can be increased only to a certain limit in order to increase the lift, and later the lift suddenly drops with the angle of attack. So it is very essential for a beginner or a designer to maintain proper angle of attack in order to have the maximum performance of the wing. So these are some of the airfoil sections. So the first one is a flat bottom airfoil, and it's a very basic airfoil. It is used for trainer planes like Cessna or Blazer, RC Blazer aircrafts, Zenith style aircrafts, and such aircrafts. Usually these have very thicker camber and flat bottom. So other one is fully symmetrical aircraft. These are used for aerobatic aircraft, so that when you turn the aircraft, when you invert the aircraft, there is so much changes in the airfoil, so that you can fly either upside down or in a normal mode. And semi-symmetrical aircraft, semi-symmetrical airfoil section. So it serves as a function of maintaining the lift and other necessary parameters between a fully symmetrical and a flat bottom airfoil. So the fourth one is under camber aircraft. The main or the usual under camber aircraft which gives very large amount of lift is S1 2 to 3 airfoil section. So this was one of the airfoil sections which we used in our projects and our aero models, because it gives the maximum amount of lift according to the software analysis theoretically. So lift versus drag. So drag is nothing but the frictional component due to the speeding of the aircraft. It mainly consists of two types of drag, such as induced drag or system drag, or drag due to the shape of the aircraft. So the graph has angle of attack on the x-axis, lift coefficient on the y-axis. So as you can see, when you this graph has been already discussed. When you increase angle of attack, the lift increases up till this peak and later it decreases suddenly. So another, we have two y-axis components. The red curve corresponds to drag coefficient. So we have another coefficient called drag coefficient, same as that of a lift coefficient. So see, the drag coefficient generally tend to increase with the angle of attack to certain points, and thereafter it suddenly increases with angle of attack. That means lift and drag has correlation between both. So we can generally say that when we increase angle of attack, the drag increases and thereby the lift decreases. So drag and lift are opposite or contrary to each other. Stall. Stall is nothing but the sudden loss of lift in an airfoil or an aircraft. So when you increase, as we learned from the previous graph, when we increase the angle of attack too much, maybe until this point, the drag suddenly increases and lift suddenly decreases. So at this point, this is called a maximum angle of attack point or stall point. If we increase angle of attack beyond this, then the aircraft stalls. That means that the lift of aircraft is lost suddenly. So this is another graph which depicts the relation between lift and angle of attack for different kinds of airfoils, such as symmetrical airfoil, low camber airfoil, and high camber airfoil. So the lift or the maximum angle of attack that can be provided for airfoil also depends on the type of airfoil. So at this stall angle, so what is stall angle? So stall angle is a maximum angle of attack at which the aircraft can fly without a stall, or aircraft can withstand the stall. And soon after, if you increase the angle by a little further after stall angle, then the aircraft stalls. So that's called stall angle. So so here's a curve for the first one is a curve for high camber airfoil. So you can see that the lift coefficient for high camber airfoil is greater than a low camber airfoil, which is also greater than that for a symmetric airfoil. So this figure demonstrates the stall point. So this is called a stall, rapid vortex or turbulent flow of air on the upside of the air surface causes a stall. So So these are some of the devices that tend to increase the lift component of the wing, such as flaps, slats, slots, vortex generators, and winglets. We will discuss each of them in detail. So let's discuss detailed stabilizers first, which provide maneuverability at low speed. So detailed stabilizers are so called because of their appearance by the T shape, as you can see in this Globemaster carrier fighter aircraft. Globemaster carrier aircraft with a T-tail. So the function of a T-tail is to keep the elevator and the stabilizer out of the wing, airflow from the wing. Usually when we consider an aircraft, the stabilizer, horizontal stabilizer or vertical stabilizer will be right behind the wing, so that when at low speed there will be a turbulent flow of air over the over the surface of the upper surface of the wing. So when this air flows over the stabilizer, there will be some maneuverability problem. But using T-tail stabilizers, you can keep the control surfaces ahead of or away from the turbulent flow, so that maneuverability can be achieved at low speeds. So here are some of the techniques to increase lift at low speed, such as rounded leading edge, sharp trailing edge. Okay, so let's move to the next slide. So wing configuration. So wing configuration is one of the main advantages of a fixed wing aircraft, because unlike rotorcraft aircraft that generates lift with the rotation of the rotor, fixed wing aircrafts can always have a multiple number of options to serve for different purposes, such as low wing, high wing, a wing with a dihedral, shoulder wing, anhedral wing, and many more other configurations can be achieved in a fixed wing aircraft. So these are some of the wing configurations in terms of the angle, dihedral angle, and the placement of the wing. So the first one, this low wing aircraft, is usually used for razor aircrafts, which has less stability and more controllability. And this is a mid-wing aircraft, usually used for sport flying, such as inverted flying. And the last thing is the high wing aircraft is usually meant for providing the highest amount of stability. It's used in trainer aircraft like Cessna. So and the last one, which is the anhedral aircraft, it's used mainly used in fighter jets, carrier aircrafts, usually this can be found in Air Force aircrafts. So the dihedral with a low wing configuration, they combine to provide stability. For example, in passenger aircrafts, usually passenger aircrafts have a low wing because of the placement of the landing gear. So landing gear can be easily attached to the underside of the wing if the wing is placed at low level. So these are some of the wing configuration by its shape, the shape of the wing. So okay, so let's talk about CG. So CG means center of gravity. It's an abbreviation. Okay, so mainly we have three kinds of CG, such as forward CG, aft CG, and backward CG. So forward CG, it's one kind of CG wherein the aircraft is nose heavy. So this can be used in trainer kind of aircrafts, which is not usually meant for taking passengers. And usually the aircraft with forward CG is usually a low speed model or a low flying model, which doesn't have much cruise speeds. Usually these kind of aircrafts have some problems, such as less stall speeds. So what is stall speed? So we already discussed in some last slides, so what is stall angle. So now let's discuss in brief about stall speeds. So stall speed is the minimum speed that the aircraft can achieve without causing stall on the wing. So usually the stall speed for this forward CG aircraft is less, means it's a disadvantage that it cannot fly very slowly. So if it reduces its speed, then the aircraft results in a stall. And also there are some pitching problems, because always since it's nose heavy, landing becomes a difficult task. It always tends to dive into the landing field, and you have some pitching problem. So to counteract this nose heavy placement of CG, you need to counteract it by applying a downward force instead of lift on the tail. So usually these kind of aircrafts have a symmetric tail section, which does not serve for any kind of components of lift, but only generates some vertical weight components in order to keep the nose up and stabilized. So this is a force diagram of a forward CG aircraft. So this is the lift component into the weight, and this is the weight of the nose. Lift is the wing, weight of the nose. So ultimately, if this force were absent, then the aircraft tries to pitch down, meaning the nose of the aircraft always points down. Instead of that, if we add this force, then the aircraft can be stabilized, and the amount of force needs to be applied here all depends on the length of this force from the CG. It's called the moment of this force about this point. So by varying the length, you can adjust the force, or for a fixed length you can adjust the force. So the second type of CG is an Aft CG. So Aft CG is nothing but the placement of CG just behind the lift center or normal horn of the wing. So Aft CG is very well suited for high speed aircraft, or the aircraft that has a high cruise speed, such as passenger aircraft that fly at very high altitude. So let me tell about one thing. If the aircraft flies at very high altitude, you know that the air is less dense there, and the lift generated by the wing when compared to flying at low levels will be very less. So in order to counteract this effect, the aircraft needs to fly at very high cruise speeds. So Aft CG is most suited for these purposes. So also the stall speeds for this kind of this configuration of CG is little more than that compared to the forward CG aircrafts, so that the aircraft can achieve much slower speeds without stalling. And also during landing there is no pitching problem. The aircraft can have very smooth and safe landing. Okay, so this is the location of CG on the aircraft, just behind the wing. And okay, this is the first diagram of an Aft CG aircraft. So as you can see, the lift component of wing will be here, and the CG will be the CG means center of gravity, means it's nothing but the point where the overall mass of the aircraft is concentrated. So so here is the net weight of the aircraft, which is concentrated. So if you analyze this force diagram, if the force on tail weren't there, then due to the lift of the wing, the aircraft would cause a pitch up moment about the CG point. So to counteract that, we need to provide this additional small lift component. As you can see, the magnitude of this lift component on the stabilizers are very much less compared to that of the wing, because the length of this force component about the CG is very more compared to the length of this force component, the force component by the lift and the CG. So again the same way as we discussed in forward CG aircraft force diagram, you can change the component of force by moving it away or towards the CG. Okay, so as we discussed in the first, these are the four components of force which acts on an aircraft. So this is I think this force diagram is usually for a high wing aircraft, because you can see the drag is well above the thrust line. Okay, so this is the thrust line due to the engine, and the drag line means is the parametric drag or induced drag from the wing. It is usually placed slightly above the thrust line, indicating that we have a high wing configuration or a shoulder wing configuration. So to counteract this, so if you have a thrust line here and a drag line here, then if you neglect these two forces, then the aircraft is gonna pitch up in this direction. So to counteract that, we provide the weight of the aircraft in front of the lift component, and the whole system balances the aircraft. Okay, so we had already discussed some high lift devices such as flaps, slats, slots, vortex generators, winglets. So now we are gonna have a brief discussion of these devices in detail. So flaps. So consider the wing platform, a single wing. I think this wing of this tapered wing, actually swept back wing of passenger or high cruise speed aircraft. So these are flaps. So there's one outboard flap and inboard flap. So and these are nothing but slats. So slats will be always placed at the leading edge of the wing, and flaps will be always extending at the trailing edge of the wing. In some larger aircraft like Boeing 747, usually you have these flaps and slats which can be deployed or external inside the wing of the aircraft. So when there is no requirement of the flaps can literally move inside the cavity that's inside the wing. So when it is deployed, the flaps come out. It really comes out of the wing and increases the surface area of the wing. And slat also performs in the same way, but in some of simple aircraft such as Cessna or Zenith, the flaps usually it will be in its horizontal position, the trailing edge. But when deployed, the flaps change its angle. It tend to rotate down and increase the camber of the aircraft. So this is about flaps or slats. We have already discussed. Slats and flaps are usually meant for takeoff and landing. So when the slat is extended or deployed, the overall area of the wing increases. Not only the area but also the camber. The camber of the wing increases, increasing the lift component at very low speed, so that the aircraft can get up into the air at very low speed, and it also requires a very short runway. So so this is flaps and slat devices in I think it's a passenger aircraft, maybe Boeing or some other such aircrafts. So these are slats which are usually present in the leading edge. So see, as you can see here, when the slats are deployed, it creates a slot here. We will discuss about the function of these slots in later slides. And so this is a flap. So here both flaps and slats are in extended position. So you can see the increase in camber of the aircraft. So this is the increase in camber, and this is another lift increasing component called winglet. So all this will be discussed just after 3 minutes. Okay, slots. So consider aircraft that doesn't have a slats or slots. Doesn't have so if an aircraft doesn't have any slats or slots, then if we increase the angle of attack at very low speeds, so here these are the stall or the turbulences caused on the upper surface of the wing. So compare with another lift, another airfoil section that has a slat, which also creates a slot in the leading edge. So if we rotate the airfoil into a same angle of attack at the same speed, Then as you can see, the slats grab the wing, grab the air in it, and as the cavity is slightly gradually decreasing as you move from the leading edge to the trailing edge. So this slot, the main function of this slot is to increase the velocity of air that is flowing inside through it, so that as the velocity of air is little higher compared to this, the velocity of air flowing directly without any slot. So this increased velocity keeps the keeps the airflow over this attached to the surface without creating any turbulence as in this. So this okay, so here you can see very clearly the slats or slot in a Cessna plane. Usually Cessna plane doesn't have any slats, so there's some special, I think it's a special model that is used to generate some high lift at low speeds. So I think it's a fixed slat wherein you cannot we cannot deploy or change the orientation of the slat. It is fixed always. So here the slat creates slots which grabs the air flowing in this way, and thus thereby increases the velocity of air that's flowing into the slot. This another small, very one or two person travelable aircraft called Untitled. So it also has a slat, because the main purpose of this aircraft is to have a very short takeoff for runway or takeoff at very low speed. Wing washout. So wing washout is nothing but the twist present as we move from the wing tip to the wing root. So this is the wing tip. So assume this is the angle, so maybe the angle of attack or the angle of incidence. So it's compare this with this value. So as you move from the wing tip to the wing root, you can see the angle of incidence of the root is a little more than the angle at the tip. So wing washout is usually meant for the purpose of serving the aircraft a wing to remove the effect of stalls at very low speed and to have controllability on the control surfaces even at the stalls. So since the angle of incidence at the root is more than that at the tip, so during a stall the root of the wing stalls first, but the tip still it doesn't stall. So usually the ailerons which are placed near to the tip, and this section of the wing doesn't stall suddenly when compared to the root, so that you can have a controllability on the aircraft roll even during a stall. So winglets, I already give a brief knowledge about winglets. So winglets have the purpose in reducing the amount of drag caused due to the vortex. So vortex is nothing but the roll or the motion of the air from under surface of the wing to the surface above the wing, causing a very large amount of drag at the tips, thereby reducing the component of lift to a very low level. So if you place a winglet, or if you place a vertical section of wing or extend it above vertically, then the flow of air from the undersurface of the wing can be regulated or checked, so thereby increasing the amount of lift of the wing. But usually these winglets are not used for low flying or low speed aircraft, because the winglet tends to increase the lift component at the tips, which creates an unwanted roll effect or the differential roll, because of the increase in lift at the tips compared to the root. Usually for a stable aircraft we need to have the lift components almost concentrated near the root and no lift components at the tips. But using winglet, this cannot be achieved, and the lift component will be more at the wing tips. So it is usually meant for high speed aircrafts such as passenger or jet aircrafts. Vortex generators. So this is a Cessna aircraft with vortex generator. I don't know if you can see it clearly. So these are some of the shapes of the vortex generators. So you will have these shapes attached to the leading edge, a little after the beyond the leading edge of the wing. So the purpose of these vortex generators are to create a turbulence. Usually we have discussed so far that we need to get rid of the turbulences which causes stall, but here is a special case wherein you try to create turbulences in order to get the airflow attached to the upper surface of the wing. So here you can see in a low speed aircraft, at the stall angle without vortex generators, it creates a turbulence. So when vortex generators are used, so the air flowing over the vortex generators creates not vortex, which creates low pressure over the surface of the wing, so that the airflow separation above the upper surface of the wing can be reduced, so that the aircraft can achieve much lower speeds compared to the one without the vortex generator. So these are some of the benefits, such as increases maximum takeoff and landing weight, shorter takeoff runway, lower stall speeds, low approach speed, high angle of attack, increased stability at low speed, gentle stall characteristics. So I think you have learned something in the field of aeronautics or aircraft design so far. So it's the time to wind up for now, and in the next video I'll discuss about the construction and the main parts of RC aircraft and the radio control, the electronics inside it in detail. So keep watching the channel. Thanks for watching the video.